Okay, good evening, all. So, I think there is no other person. Okay, so only me. Let's start with the whatever we discussed in the last classes. So, first of all, we discuss about the why the chirality is so important to our to nature. So, we discuss about in the last class we discussed about why chirality is important. It's so important. Next is that we discuss about the to recognize the molecular recognition. So molecular recognition is the one of the most important thing in our nature. Molecular recognition. Recognition. Just a minute. It's having something issue with that. Okay, fine. So molecular recognition. And third thing is that what is the origin of chirality? Why the how the chirality comes into the picture? So origin of chirality. Okay, origin of chirality, and then here comes the how the all the amino acids and carbohydrate and DNA, RNA, all those nucleic acids, protein, protein or amino acids, then carbohydrate, carbohydrates, nucleic acids, and fourth is the antibacterial reagent. Okay, so so far we discussed about those things. Now the question is, what is the origin of the chirality? How the chirality comes into our Earth atmosphere? So my major question is, so from where this chirality comes into the picture? So chirality is tool for the biology can actually taking the responsibility to recognize the molecules all and further involvement of that molecule into the nature. So So chirality is nothing but we know about this. This is the non-superimposed the molecules having the non-superimposable mirror image to it, and that molecules become the chiral. So now question is the how we can make these chiral molecules. First, as we previously discussed, the chiral molecules only when we can produce in a specific one specific isomer by the using of help of enantio by the chiral environment. Otherwise, we cannot detect the chiral molecule in a chiral environment because of the chiral molecules. Chiral molecules has two kind of isomers. One is that, let's suppose one is the A isomer, another is the B isomer. So these enantiomers are show the similar physical and chemical property into the chiral environment. Whenever we place this chiral molecule or all those enantiomers into a chiral environment, they can behave different. Their property, their chemical property, their physical property also can differs in that case. Let's suppose we have some uh, chiral molecule. Let's suppose what is that? L amino acid. Whenever you are we have the D amino acid into it, and that is the mixture is the L and D is 50-50%, that becomes the racemic mixture. Whenever you place in the chiral environment, let's suppose in our body enzymes, all those things are chiral in nature. Whenever we place this amino acid into our body only can take the L amino acid because of the chiral, the molecules recognized by our body only the L amino acids. So our body can consume only L amino acid. That is the major factor. So we discuss about that. Though we need to recognize a chiral molecule, we also record the chiral environment. And also we can nature also producing huge number of enantiomeric excess. What is enantiomeric excess? That means we have two enantiomers. One of them, whenever synthesizing these enantiomers, one of them are predominantly producing into the nature. So why this is happening? So because of nature actually using that, taking help of the chiral environment to produce those uh, chiral molecule and chiral excess chiral molecule. So now question is, in the first of all, we have to produce the whenever our earth is actually developed, that means it is a huge warm or a hot earth is there, and then it starts producing different kinds of organic molecules like different amino acids, carbohydrates, all those things. So there's requires initially there is nothing in chiral in nature. Then the first of all, we need the chiral environment to produce a one particular chiral molecules. Otherwise, it becomes a racemic mixture. We cannot differentiate these things. So for that, we need a chiral environment. So the chiral environment comes. There is some theories. Some theories is that that is called this chirality actually comes from the out of this world. So how people are discovered that this chirality actually found from outside of this world actually. So now question is that this chirality actually induced from outer side of the mind earth. So first chiral molecules comes comes into the earth. It is actually out of the world, out of the this earth, says earth atmosphere or earth ground. So now we were in the question is the origin of chirality chirality in earth. So the to answer these things, we actually saying that this chirality comes from the from extraterritorial body, external body. Okay. So what is the proof that? So why we are saying that this chirality comes from the external body? One proof is that it is called, so that is called Mar- Murchison meteoroid. The proof of the this chirality comes from the external body, that is Murchison meteoroid. This Murchison meteoroid actually named by the one place is called Murchison, which is actually placed in the Australia, Australia, and place is the Murchison place. Sorry, Murchison, Australia, Murchison. So this meteoroid actually comes from the, we know all those know this meteoroid actually come from the out of this earth system, and it's fall into the earth. Sometimes they are actually burned into atmosphere because of friction of the atmospheric molecule. And if it is too large enough, that can fall into our into the ground. And somehow these Murchison materials survived to around 100 kgs, around 100 kgs of asteroids into the ground, and scientists found into take into the laboratory, and they test this meteoroid, and they found along with the some molecules, some atom, some other molecules like sulfur molecules with containing carbon, sulfur, phosphorus, oxygen, nitrogen, all those things. Along with, they found some different organic molecules, and these organic molecules containing some carbohydrate, proteins, specifically amino acid. They found lots of amino acid into it, and some of amino acids are different in nature, which is not exactly found into the our earth, in our nature. So in that asteroids we found so lots of amino acid, which is actually available in our atmosphere. So amino acids, all those found actually, serine, serine, which are found, glycine, sorry, glycine. Then we have alanine, glutamic acid. Further is that leucine, valine, valine. Okay, and so all of them are present in D and L isomer. L and D isomer also found. isomers are found, but where the L is the predominant enantiomerics found is found as enantiomeric axis. Okay, so these L isomers all are actually found into our nature, but also there is a presence of the DNA D amino acid into that meteorite. That means this amino acid actually comes from the it actually synthesized in the out of the world, and that is coming to the our earth crust, and and inducing this kind of amino acid into the earth crust and generates a chiral environment to produce a chiral molecule into the atmosphere. That is the starting point of our chirality in our earth crust. So along these amino acids, they also scientists also found some defined amino acids, which is another derivative of serine, some other amino acids. So these are not the straightforward amino acid. It is a derivative of serine. Serine, which contains a hydroxyl group, which is where the R equals to CH2OH, but it has a different structure. Now, another, what are the different amino acid they found? There is a, we have some. This is C double one OH. And here is the here will be my OH, and this is the NH2, and this will be the my chiral center, and that is named as isoserine. This is the isomer of the for the serine is that here will be the NH2 and there will be the OH. Now this is the isomer of the serine. This is called isoserine. Okay. Now another isomer of it where that another CH2 group is there in here. So we have this is the group, then OH. CH2 CH2H, and there is a NH2 over here. C dot H. This is my chiral center, alpha carbon, and this is called homoserine. Homoserine. We have another isomer of it. We have here is that COOH. Sorry about that. This will be my structure, and here is the OH group over here, and here is the H2 group over here, and this will be my CH3. This is called isothreonine. Isothreonine. trio isothreonine, and also it has another isomer where the this is the OH group below the plane. This is the NH2 group above the plane. Where is the CH3 group? And this will be my COH. This is called Ella isothreonine. Ella isothreonine. Okay. Now some other organic molecules. This another kind of amino acid. For this, A is not connected. Amine is not connected with the alpha carbon of the amino acids. So there is some other organic molecules amino acid which is over here. This will be COOH. This one is the this one is the OH, and followed by this is the NH2, and this one my the alpha carbon, and which is actually chiral in nature. And then to name it, we have this called as 4 amino 2 hydroxy 2 hydroxy butyric acid, butanoic acid, butyric acid. Because of this is the 1 carbon, this is the 2 carbon, this will be my 3, this one will be the number 4 carbon. So to it, so 4 amino, that is 4 is actually connected, amine is connected with the carbon number 4, and 2 hydroxy group connected with the carbon number 2 butyric acid, that is that name. And in small letter, it is in the small, it can be denoted as 4A 2 HBA. Because of butyric acid, H is the hydroxy butyric acid, that is the 4A2HBA. Similarly, it has another is that COOH. In the third position, we have the OH group at carbon number 3, at the carbon number 3. So this one my 1, 2, 3, 4, this name, and this was my the chiral center, and then this is named as 4 amino 3 hydroxy butanoic acid, butyric acid. In the short form, it should be called as what will be 4A 3 HBA. Okay, so this is also found in that asteroids. So some other also organic molecule which is called beta homoserine. Beta homoserine. which is what is the structure of that. This is the COH over here. This is my NH2. This is my OH, and this one will be my chiral center. This is called beta homoserine. Another is that we have COOH. This one we got OH, and this one we got NH2. This is named as 3 amino 2 hydroxy methyl 2 hydroxy methyl propanoic acid. Propanoic acid. In short form, it is called 3A 3A 2 HPA. Similar to this one, there is another molecule. This is COH. This is NH2. The alpha carbon, there is NH2. There is a CH3, and this will be my OH. So in that serine, the CH3 actually replaced by the hydrogen only. So it is named as the alpha methyl serine. Serine. Okay, and then we have another is that beta amino methyl succinic acid. What is the succinic acid structure? Structure is the succinic acid is the COH, and there will be my COOH. This is the structure of the succinic acid, and then we have NH2 over here. So this is my chiral center, and this is named as beta amino succinic acid. Okay, so these amino acid actually found along with our natural amino acids. So we actually able to found that these asteroids actually contain lots of amino acid which is not generated into the earth crust. So it is extraterritorial bodies which is coming from the out of this earth, and it may be in from the solar system, maybe out from the solar system. Actually this meteoroid, after examination, this meteoroid actually found is around its formation of this meteoroid around beyond 4.5 billion years ago. In that time, actually, our solar system actually formed. So during that time, these asteroids actually formed, and this amino acid actually contained from that time also. So it means that this chirality actually induced into our earth crust actually from the extraterritorial bodies. So this is these asteroids, huge number of asteroids actually come into our earth crust. It forms a chiral environment to synthesize a new molecule. We have the chiral environment over here we are producing, it can prefers only one isomer whenever they are producing synthesizing some chiral molecule. Let's suppose we have some chiral environment, and that is actually helping to produce the D-glucose. So only D-glucose actually producing in furthermore they are actually producing some different D-glucose, different isomers. And on particular system, nature actually mutated to something some way to found another isomer for its records. So from meat, this enantiomer axis actually comes into the picture, and is producing the in a the chirality into the nature, which is actually induced from the extraterrestrial body. So this kind of amino acid found in asteroid actually provide the idea that these extraterritorial bodies actually triggers the peptide, one particular proteins formation of one particular proteins into our environment. So and that creates the chiral environment into our earth crust. Okay. Now now our question is, so in our we are actually discussing about the optical activity and the CD spectroscopy. So how the optical activity actually comes into this chirality, all those things, how the optical activity related to the this chiral molecule. As we know that we have the chiral molecule. So to detect the chiral molecule, we need a chiral environment. So chiral molecules, is the our light is chiral? To detect that chiral molecule, our question also arises that we know that to detect the chiral molecule, one particular chiral molecule, we need a chiral environment. Otherwise, you cannot distinguish the chiral molecule because of its chemical and physical property similar. So, because two isomers, two enantiomers, chiral physical property is similar. So, sorry about that. The chiral molecules we are talking about. So, with that, so what is that actual interaction between the light and my chiral molecules actually happening over here? To understand that, we need to little bit focus onto that. What is called what is called light matter interaction. It is a completely quantum mechanical part, which is called as light matter interaction. Why it is called so? As we know, some molecules is absorbing the light, and its electronic structure, it becomes absorbs the light. Initially it is molecules in ground state, and whenever it's absorbing light, it excited to its excited state. But we are thinking about something that our we are shining the light, we have our electrons at the ground state, which jumps to excited state. That is not happening. That is a different thing. This electron cannot jump. Our thing is, so what we are actually initially talk about, that we have our, this is the energy, and this is my ground state. It is the ground state. We have one electron over here, and it excited to its excited state. That is the jumping we are thinking about. This is excited state by the shining of light. So is this electron actually jumps? No, this electron is not jump. The electronic orientation, something like that, the energy state of that molecule actually at the excited state, which is matches with that, with the energy of the excited state. So in that case, we are thinking about this energy of that excited state should be something like my electron is distribution, something like where my molecules over there. This will be my energy. Okay, so how it is happening? So this is a completely quantum mechanical phenomena, as we know about the Schrodinger equation. So this is my Hamiltonian operator. This is the psi. Let's suppose it is called as a ground state of psi. This is a function for the ground state. It's large. This is my ground state wave function, and it gives me the E ground state and the wave function of ground state. Now there is a perturbation. We are providing some light, sunlight, some providing some H over here. It may be my radio wave, maybe microwave, maybe IR wave, maybe UV, maybe X-ray, maybe my gamma ray, depending on gamma ray, depending on which transition we are actually taking care of. Let's suppose now we are exciting to each different state. In that case, our Hamiltonian operator should always changes because of that the excited state. In that case, there are all those parameter for the my my molecule, my orbital, my every orbitals which is actually in defined in nature. So that should be excited to a different Hamiltonian operator which is called H dash. We are talking about this is the H dash, and the wave function also changed because of the shape of the our electronic orbital is different in that case. So that too is called excited state, which is excited state and gives me energy of the excited state. And furthermore, we wave function of the excited state. So this perturbation actually gives me the light matter interaction happening through the absorbance of the different light. It may be radio wave whenever we are talking about the NMR spectroscopy, where we actually talk about the radio wave. If it is my rotational spectroscopy, then it will be the microwave. If it is vibration frequency, we are talking about vibration of the molecule, that it will be the IR frequency. If it is the it is the electronic electronic distribution in their orbital, then it will talk about the UV spectroscopy, ultraviolet, that is uh, optical spectroscopy, where and then we have the electronic distribution. Let's suppose we our inner cell electronic distribution talking about, then it will be the X-ray. Its gamma ray is the nuclear distribution whenever we are talking about. Will come into the gamma ray uses of the gamma ray in the later part of this course, that is the Mossbauer spectroscopy, which is gamma ray actually used for the nuclear perturbation to detect the what is my molecules and how it should behaves in that Mossbauer spectroscopy. Okay, so basic fundamental is that we have something like electronic distribution in an orbital, which is, let's talk about, this is my ground state. This is let's suppose this is my orbital. Hypothetically, don't think about the actual orbital. So this is my ground state, and we are perturbing this by the h nu, and it becomes this thing. This this is the excited state, and This is always called as the star, and this is the star. Sorry about that. This is star, and this is the wave function x state, and this is my psi of ground state. Okay, so by the help of the perturbation, that is the h nu. H nu means we are providing some radio electromagnetic wave to perturb my system to generate a new excited state, which wave function is the psi star e excited state. Okay, so this is related to that my by perturbing my ground state to excited state, which is actually fundamentally actually providing some energy state of the electron molecules, which changes to one ground state to excited state. Okay, now question is that how this light actually affect to perturb my molecules. What is the question? Now question will arise. mm, Question question is how this light actually perturb my molecules. That is the major question we found right now. To answer that, we have to think about what is the light. What is the light actually talking about? We know light is a nothing but electromagnetic radiation. Light is a nothing but electromagnetic electromagnetic radiation. Okay, we have the light, which is actually combination of electric field as well as the magnetic field. So it is associated with the two part. One is the electrical field, another is the magnetic field. Electric field as well as the magnetic field. Okay, so this is called as the E, this is called B. So in all these electric field and magnetic field, they are actually oscillating perpendicular to each other. So how it looks like, it's been, we have, this is my electric field, let's suppose, and this will be my magnetic field, and this will be my propagation. How this is propagating to, this is my E, this is the B, and this is my direction of the light travel direction. Okay, so this is we are showing the one particular direction, so that actually looks like we have, this is my, let's suppose. And here more interesting thing is that this electric field is a very strong field. and magnetic field is the weak. So that's why we are showing the amplitude of this electric field and magnetic field are different. So in the real time, how it looks like, we have, this is my wave, maybe sinusoidal wave. We are talking about, this is my electric field propagating to this direction. Sorry of my drawing. And then we have the color is that perpendicular to the this. What time to do this? We have these things. This is perpendicular to the, these are not the direction of B, and this is the direction of the electric field E. This one is the B. So actually propagating. So electric field and the magnetic field associated with the electromagnetic wave. Now question is, so which part will be the actual responsible for for the the light matter interaction? Okay, so as we know, in the molecules we have the electronic distribution, which is called as a dipole moment. Furthermore, it can be called as a, as we know, that is the polarizability. This polarizability actually responsible to interact the light to the molecules into that into the systems. So this electric field actually change the electronic distribution. As we know, we have the electric field, we have some electric field of molecule because of its polarizability, as well as the polarizability contains the dipole moment. This dipole moment actually responsible for the interaction between the electric field and the molecular dipole moment. So for the note is that electric field actually, the electric field change the electronic distribution at the molecular level. Change the electronic distribution distribution and which is related to the called is polarizability. Polarizability, which is denoted as mu. Mu is that polarizability which is associated with the electric field followed by polarization, and which is, this is the polarizability, and this is the dipole moment called dipole moment. Just a minute. We need another slide. Okay. So where we was? This is the thing. And this is the my dipole moment, and the transition happens. We are providing light. It's generated if the electronic structure of the molecules actually changes, and it becomes the at the ground excited state. When this is happens, there should be some certain point, certain criteria which is actually fulfilled over there, and that actually gives the result of the this transition. That is called transition moment integral. This is a completely quantum mechanical term. This is this transition happens only when this transition, how this transition happens. This dipole moment integral, that is the probability of this transition, probability of the electronic transition, which is actually denoted by quantum mechanical term, which is probability density. Yeah. Oh my god. Okay. This will be plus infinity to minus infinity. My overall integral will be overall integral, that is called my psi excited state A star followed by transition moment, dipole moment, and then we have ground state psi, and integral over all over the space d tau. When it should be becomes 0, another time it should be 1. So when it is 0, that is called forbidden transition, and this will be called allowed transition. Okay, allowed transition and forbidden transition. So how this term actually comes, the why when this one transition is allowed or forbidden, is actually depends on the which part actually associate with this mu value. This is the major part which defines actually my transition is allowed or not. When it show the allow, it's that means this overall integral is 1. There should be some certain phenomenon, certain criteria for the where the um, that is my transition forbidden or allowed or not. That criteria actually defined. Let's suppose we have some. Let's suppose electronic transition happens in a DD transition. This is for the D5 system and high spin, that is manganese 2 plus. We'll see that the manganese 2 plus, the solution is very pale pink color because of this transition is the DD transition. Further, this is spin forbidden as well as the orbital forbidden. As we know, the GD transition is the forbidden orbital forbidden transition. Only sometimes it show the GG transition because of the spin allowed transition. In the D5 high spin system, this spin forbidden, this transition are spin forbidden as well as the spin orbital forbidden transition. So that's why the D5 high spin system always so very faint faint or nearly about the colorless solution. Its transition moment in trigger sometimes is zero because of it's not be zero because of there's some if it is absolutely there is no vibration over associated with that electronic spectrum, so then it will should be zero. But some we are getting some data because of the spin orbital coupling as well as the vibration, which is actually so the say which is give provide the loss of symmetricity into that system, and then it becomes some little allowed transition. So for that we are getting some uh, pale pink color solution. Okay, so so depending on this transition moment integral, we can uh, say this is allowed or forbidden transition. So first of all, to thinking about there's thinking about the optical activity. So that should be optical activity. That means we are talking about the UVB at the UVB region, the light is absorbing or not, or light matter interaction into the light region of the UV visible region. So which is actually associated with the uh, light absorbance of by the molecule, light absorbance by the molecules. So this is the one term is absorbance, light is absorbance, which is called FA, which is denoted as the epsilon. C is the concentration, L is the path length of the light passes through. Let's suppose we have some cuvette over here which is associated with some solution, and we have passes through light, and it's initially my incident light is I0, and I0, and this is the after incident, another after incident this becomes the I. So this absorbance is actually a logarithmic value. It's called log of I0 by I. So this is a ratio of the I0 and I, and that why if as it is ratio and the logarithm value, this is the unitless parameter. Unitless parameter. Okay, we have solution. We are shining the light one part of the cuvette, another part of the cuvette we are getting some light which is actually transmitted to from the solution, and ratio of that solution actually called the absorbance plan, which is logarithmic of this ratio of this incident light and the outcome light from the solution, which is actually called absorbance. So for this is called absorbance, this is called concentration of the solution. It's actually pretty uh, associated with the amount of molecules, that is the concentration, and its unit is the molarity, and this is the my path length, and this is my centimeter. So in that case, epsilon is called molar extinction coefficient. Extinction coefficient. So it is actually depending on molecules. It is a parameter. It is intrinsic parameter of molecules. Also depends on the temperature as well as the wavelength of the system. Shining light. Okay, how it is depends on, we have some molecules. Let's suppose we have molecules. How it is actually associated. This is my molecules. Okay, we are providing some H nu. This is my H nu, and then as you know, this become excited. This is the H nu. So and this matter actually contains some. This is the particle we are talking about. It contains its wave function over here, which is associated with the wave function. This is ground state. How it looks like, so it can be look, say this is my wave function, and we are actually perturbing this wave function with the some external perturbation, which is sine is new, and followed by we are actually generating some different wave function, which is, let's suppose this one. Okay, so this is my psi star es, and this is the psi ground state. And how much this interaction happening with this wave function of the particles and the external perturbation, which is depends on the called as called as the oscillatory transmission, called as oscillatory transmission transmission. Depending on the oscillatory transmissions, we actually get a new wave function, and how much its oscillation happens, that is depending on the how much oscillatory transmissions happen into the this wave function of the particle, and that is called oscillation or oscillatory. This function is associated is called oscillatory function. Oscillatory function. Okay, oscillatory function. This oscillatory function actually redistribute my electronic distribution into the molecules. This process actually redistribute my electronic structure. So this oscillatory function can be denoted as, this is called frequency electronic. It is called 4.350 into 10 to the power minus 9 followed by integration of nu 1 to nu 2. That means we thinking about this is the nu 1 to nu 2, nu 1 and nu 2, depending on the let's suppose no, not this one. And then we have the molar restriction coefficient, which is completely dependent on the nu followed by d nu. So we have some initial part. Let's suppose we have initial one is the energy. We have the nu one over here and nu two over here. Nu one, nu two. Our energy distribution of the wave function is something like, oops, this will be Gaussian type. Okay, so this is my Gaussian type. Now we are shining the light. It's redistributed to different. It's redistributed to different, and it's forming. This is my new wave function. So this is depending on the how my epsilon is actually behaving into that wavelength, but new in that wavelength or in that frequency region. So with respect to that, in our optical spectra, there's some transition presence, which is in the molecular level. We have, as we know, we have the pi to pi star transition. We have n to pi star transition. We have some dd transition, spin for allowed dd transition. We have spin forbidden, orbital forbidden, dd transition in case of d5. And depending on all those data, so this is actually greater than 10,000. So one more thing is that, as we know, the epsilon is a by cl. So the unit of epsilon will be mole in molarity inverse and the centimeter inverse. So depending on that, this will be more molarity inverse, centimeter inverse, and this will around 10,000 to 5,000. This will be my around 100 to 1000, and this will be 0.1 to 10. So, and MLCT actually fall, MLCT and LMCT, charge transfer transition, which is actually fall in between this MLCT, LMCT or MMCT. MMCT is the metal to metal charge transfer, fall into this region. So so why in case of d5 we, this is the spin allowed, this is spin allowed, spin allowed, but orbital forbidden. This is spin and orbital forbidden transition is, we talked about that manganese d5, that is the Mn2 plus octahedral. This is spin forbidden as well as the orbital forbidden. DD transition, all are the orbital forbidden. And this for orbital forbidden, sometimes orbital allowed when becomes whenever its vibration happens, the bond stretching bond frequency or have bond stretching bond stretching happens, and the it lost its what is that symmetricity, and then it becomes a orbital allowed. So sometimes we get some good data for that. In that case, the D5 system, this is the completely spin forbidden and the orbital forbidden, but somehow we are getting the epsilon value around 0.1 to 10 mole per centimeter inverse because of the vibration of that ligand to metal bond. Okay, so so electronic transition actually. So with that, we can say the electronic transition of the molecule, which is actually happens due to the light matter interaction. But that in that light there is a two field. One is the magnetic field, another is the electric field. That electric field actually responsible, major responsible for the electronic redistribution into the molecules. And depending on that uh, interaction, we can some define some polarization or polarizability, which is mu actually equals to that depending on the polarizability and the electric field of that of the lights. Okay, so so where we can say this is my optical optical spectroscopy, which is actually depends on the absorbance, which is actually associated with the absorbance of the molecules by the absorbance of the light by the molecule, and which is actually depends on the a relation called Beard-Lambert's law, which is where it is. This is called Beard. Oh, change the color. This is called Beard-Lambert law. This Beer-Lambert law associated with the epsilon value, which is called molar extinction coefficient, which is actually completely depends on the molecules to molecules, and and the followed by the wavelength of the molecule, wavelength of the shining light, and depending on that, we can say which transition happen. Is it pi to pi star transition? Is it pi into pi star, or is it DD transition? Or is it MLCT or LMCT or MLCT? Depending on that, and there is some value of that epsilon. Uh, with respect to that, we also can say that this molecule actually absorbing light around this region because of that particular transition. Okay, so now coming to the another thing, plane polarization thing. So in the optical activity, we have to use the polarized light. Okay, so we have some uh, picture over here. This is the picture. Or let's talk about these things. First, we have some unpolarized light. Unpolarized light means, let's suppose we have the electromagnetic radiation, short-term electromagnetic radiation, which is actually propagating something like this. My electric field and my magnetic field is perpendicular to it. This is the B, and this is the E. Okay, so B and D, which is actually perpendicular to each other. And let's talk about we are only here only we are talking about the electric field. So my electric field is propagating like this. Okay, so if we look from that direction. Suppose this is our eyes, and from that direction, how it looks like? So it looks like, and light is actually propagating, oscillation happens in that direction only. Okay, so we have one particular part. Let's suppose we are thinking about this one and this one. So how it looks like, over here I'm writing over here in this direction. We have, this is my maxima over here, maxima here, and then followed by another maximum. So this is my center we are thinking about. So let's suppose here is the point A, here will be the point B, here is the point C, the point D, here is the point E, sorry, E, this is the point F, G, H, and followed by I. So this point A is directed this way, 0, and then we have this way, sorry, this way. So like this is the my major part, maxima. We have down direction, this is the point, C point will be the point, then it will my negative direction, and there will be some maximum negative, followed by again it goes down, this will be the my point, then again rise up, and the maxima over here. So if we superimpose into this, we can find only these things. This is the maxima, and then this is the point. So this is how actually it looks like the light. So that's why if it is in one particular direction, we have the unpolarized light. This is the polarized part. The unpolarized light right now, what we have the all of direction over here. This is the direction we are right now talking about. It can also move in that direction also, that direction also, this direction, all possible direction we can talking about. More interestingly, this is the unpolarized light, polarized light. Whenever we are passing through in a crystal, it is the polarizer we call crystal, polarizer crystal, where we get a polarized light. Okay, this is polarized. So in that polarized light we have, this is my unpolarized light, this is the E we are talking about, this is the unpolarized light. Whenever it passes through in a polarizer, it can only allow the lights which is actually oscillating, the electric field of that light oscillating to that z direction, which is over here. This is the E, and this is the called is plane polarized light. This is called E, is called plane polarized, plane electric field. This is E is the electric field, plane polarized light. Okay, so whenever this plane polarized light pass through that sample of solution where the my optically active molecule is present, which actually rotates this plane of polarization electric field of that plane polarized light in a certain direction. this certain direction actually, which is actually deviated from our initial position. From that we can calculate the what is the amount of degree of rotation has been done by the this optically active molecules. Okay, so that's how we are actually found the optical rotation, amount of optical rotation. Now more interestingly, we have this optical active molecule should be, this is the optically active molecule which is actually chiral in nature. That should be chiral and enantiomeric exit. If there is racemic mixture which is enantiomeric, we should not get any optical activity. Meric excess. That should be enantiomeric excess. Otherwise, you cannot find the optical activity. Okay. So now question is this: why this? Let's suppose we have some molecules which have a two different isomer. Let's suppose we have chiral molecule, chiral molecule, and we have two isomers. One is the A, one is the B. If A rotates the, if light rotating by we're talking about this direction, we have, this is the my initial position, and light rotate this direction. If that is plus theta degree of q, not theta degree, B should be rotate light the around minus theta of theta degree. Okay, so one isomer should rotate theta plus theta, another is the minus theta. Now question is, so is this light is chiral? As we know that to detect the chiral molecule, we need a chiral environment. Now question arises, is the light chiral? Is the light chiral in nature? This is the my major question. Answer is yes. How? There is an interesting phenomena is there. The how is this happening? Let's suppose this is our plane polarized light. We are talking about, this is the plane polarized, this is the center, the plane polarized light, which is actually associated with the two different light. One is, we are talking about, this is, let's suppose this is my light over here, two circularly combination of that two circularly polarized light. Talking about this thing is 5 atoms. Okay, this is thing, this is thing. Okay, we have initially of my thing was this direction. Okay, okay. And writing in a different color. Okay, initially my thing is that over here. Let's suppose initially my thing is this direction, and further this is rotating this light this direction. This is the combination of the two circularly polarized light. Now, this is the direction of the rotation is that this direction, and we have another one is that by right hand direction. Okay, we have this all those things. Now, question is question is this is light is actually rotating in that direction. That means it is left-handedly. So it is called L left-handed circularly left hand circularly polarized light. Left hand circularly polarized light. Okay. So in short term, it's called LCP. LCP. And this is called RCP. Right hand polarized light. RCP. Okay. So now we can say let's talk about this plane polarized light divided into two direction. One is the left hand circularly polarized light, and that is the right hand circularly polarized light. So if you think about this is my proper direction of the light travel. This is the light travel. So how it's actually this plane polarized circularly polarized. This is the direction how this is actually travel. This polarization happens. If it is combined together, it actually forming one direction, that is that. And this is my right handedly polarized light, and this is my left hand circularly polarized light. Okay, this is the direction of the propagation. Same way also. Same over here also. So these two are mirror image to agent, non superimposable mirror image. Impossible mirror image. Okay, so that means my left hand circularly polarized light are mirror image, non superimposable mirror image of the right hand circularly polarized light. So that means this LCP and RCP chiral in nature. So so individually LCP and RCP are chiral in nature. Okay, so if my LCP and RCP chiral in nature, that means we are providing some chiral environment. So my plane polarized light divided into one called combination of the LCP and RCP, and and the my my light propagation actually one right-handedly and another is the left-handedly helical structure. So my LCP and RCP now becomes the helical in nature, and that is the mirror image to each other. Two different helical is there, so they are chiral in nature. We have the chiral environment, we have the chiral molecule, so we can detect it easily. Now question is that there should be some parameter. Which parameter actually defines this optical rotation? Let's suppose is that molecule my molecule interacting similarly to the left-handedly circularly polarized light or right-hand circularly polarized light? Now question, the answer is that no. My one particular enantiomer actually interact more with the one particular circularly polarized light. Now the possible way is that we have some LCP and RCP over here. We have molecule to the molecule interaction. Now we have RCP over here, and we have LCP over here. This will rotate towards this direction, and this will direct directed towards this direction. LCP. Okay. Then overall polarization is that we can write it in the black. This is the my plane light of plane polarized light. Okay, we place the sample over here. Sample over here. Let's suppose my one the traveling of this LCP and RCP is different in that case. In that particular through this sample, it is the different. Let's suppose we are here. My left hand circular color, different color. So let's suppose this is my left hand circularly polarized light traveling in particular time. This is the time direction we are talking about, time. And we have different over here for the left hand one. Okay, so let's suppose this is travel slowly, very slowly. um, Travel direction is opposite to each other. That means it is lower, and then we in that direction we only pass this part only, followed by this part. And in that case, this actually pass through this that much. Now we have this much. In that time, it actually goes this direction. The speed of light RCP is different. So we have this is the RCP. This is LCP. LCP. So speed of light in the medium in the medium is different. Sorry, are different. LCP and RCP. So which is actually associated with the refractive index of the solution. Refractive index of the solution. So as we know that my travel speed of light in on particular polarized light actually defined in that molecules. So that means let's suppose here we can say the interaction between interaction of the LCP and RCP is different over here, and then LCP is very slow. So that means we can say this is the uh, low, or is that slow? That means interaction high, high interaction, high interaction, and over here it is low interaction. Okay, so overall result we get over there, we can say that this is my, and if you project it, my initial one is the year one. If you project in between this, so my theta will be this amount. Sorry, I'm trying to change it in a different. We have, oh, we are talking about black one. We have my plane polarized light over here, position in that direction initially. Now we have left hand circularly polarized, right hand circularly polarized light is around, travel around in that direction that much, and left hand is that different amount. Okay, so the projection will be the in between, that will be my actual rotation. So this one is the actual rotation. So this amount is called theta. It's the degree of rotation. It's called degree of rotation. Amount of, sorry, this is the amount of rotation. This is the amount of rotation. Okay, so this is known as the optical. This phenomena is called circular bifringes. Bifringes. Fringences. Okay, for the, for my LCP and left hand circularly polarized light and right hand circularly polarized light travel in a different speed, and which is actually associated with the refractive index. This is one mathematical term ever connected with that. That is that optical rotation happen only when the refracting index of the LCP and RCP is the different. Theta refracting index of L or not equals to refracting index of R. Okay, and then so that is the optical rotation phi, which is actually initially what is denotation. This will be my phi. Phi. So phi is phi proportional to my eta R minus eta L, and also phi can be denoted as 180 L R by lambda, and phi actually depends on the lambda and the temperature, which is actually phi of C and L will be. Okay, so this is my mathematical term we found over here. This is phi is the amount of rotation. This is eta is called refractive index of refractive index of circularly polarized light. Okay. And this is phi is the optical rotation, C is the concentration of the solution, concentration of the solution, L is that path length, and we have something called, and this is the polarized parameter where unit should be in decimeter. And this phi is a specific rotation. This is called specific phi lambda t is called specific rotation. It depends on temperature as well as the wavelength which is used. Okay, so this is the mathematical term. We have some mathematics onto that with respect to here. I will solve it right now. We have one mathematics over here, which is that just a minute. We have a call. Okay, sorry about that. So we have this mathematics over here. This is my mathematics. Let's try to solve it this one only, which is called the one sample is containing a single enantiomer. First of all, we have to note that there is a one enantiomer present over here. Single enantiomer, the that is actually fluoxetine, which is placed in the polarimeter, that is the instrument, and the observed rotation is 9.06 degree clockwise. That means RCP we are talking about. The and that RCP is the higher speed of light is right-handedly, the right-handed direction is high. Okay, the sample was made dissolving the 1.24 gram in fluid fluoxetine in solution, which is total volume is 2.62 ml, and the light source was sodium D-line. That means that means beyond the 800 degree, 800 uh, beyond the 800 nanometer region, and then the temperature is 25 degree. The length of the sample was 1.25 decimeter. So everything is given. We have, that means we have phi equals to, sorry, see. So everything is given. We have phi, which is actually 9.0606 degree. We have C. We have to calculate it. C. We have 1.24, and wherever we was, this C unit of C will be gram per ml. Gram per ml. Okay, and then C is the 1.24 over here, and L is the 2.62. Okay, this is the gram per ml. Sorry, and you have the path length around. L is that 1.25 decimeter. So it's very easy right now. We have to calculate the specific rotation, which is actually phi, and that phi, the d lamp 25 degree. We have to write it 25 degree. See, and d lamp per, which is to calculate phi specific. We have to calculate specific rotation C into L. Now we have to add all those data. 9.06 degree divided by C is the 1.24 divided by 2.62 and followed by 1.25. Okay, to calculate it, it's very easy. Now the result is the 15.3 degree. Now we have to provide the unit over here. So this unit will be gram inverse, ml inverse, ml, and the decimeter inverse. Okay, this is the specific rotation we found with their mathematics. Depending on this equation, we can calculate the, what is that, my optical rotation of the molecules. Okay, or specific rotation or optical, how much, if that is specific rotation given to us, we can so on and so forth, we can calculate the how much rotation we can observe from the polarimeter, as well as the, depending on the specific, we know the specific rotation of the particular molecule. Let's suppose we have sucrose has a specific rotation around 55.6. So depending on the specific rotation, we know the concentration. We have to calculate. We know the path length of a tube or the optic light actually passes through that amount. We know the specific rotation. We know the rotation how much we can get from the polarimeter. With respect to it, we can calculate the, what is, we our actual concentration present of a particular solution in a sucrose solution. So unknown solution concentration of a sucrose solution we can determine very easily. Okay, so this is the way we can use it. This that way, truly speaking, this kind of experiment has been done in our undergraduation level. So we did it in our college. So over there we performed lots of polarimeter experiment. That is determination of the specific rotation of a particular molecule, as well as the unknown sample to know the concentration of the sucrose solution into the unknown samples. Okay, so this is how to it. So we can stop over here. Whatever we actually discuss about, let's sum up over these things. First of all, we introduce what is the origin of, how the first actually uh, origin of chirality comes into our earth crust. Origin of chirality, which is actually chiral environment, comes from the extraterritorial, external Exter- sorry, external bodies. Second thing is that these external bodies actually contains lots of amino acids. Now we actually discuss about the light matter interaction. Light matter interaction, which is actually associated with H psi to E psi, psi ground state, ground state to resigning the light. We are actually making excited state one, that is H dash I. So H dash, H dash and psi excited state is to E of excited state and H dash and psi excited state. Yes. Okay. So this perturbation, this is the perturbation by the light. Okay. Now we discuss about three. Discuss about polarized light, plain polarized light, polarized light. Furthermore, you can call it circularly polarized light, polarized light, which is LCP and RCP. Okay. We actually discuss about the optical activity. Optical activity, which is actually phi lambda t equals to phi by c, but the c is the concentration and L is the path length, and this is the degree of rotation, optical rotation, optical rotation, and this is the specific rotation, specific rotation. So these much we actually discuss about today. So next class onwards, we'll actually go through into the this how this circularly polarized light actually interacting. If here we are actually mostly showing that the light actually speed of the light is different through a solution where the my chiral molecule is present. If sometimes this light speed of light is different over there, we are saying we can get the optical activity, that is the circular by fringes. If the light is absorbed, one particular light is absorbed, how it looks like one, that is the circularly LCP and RCP absorbed in a defined way into that chiral solution, then how it looks like, that we will discuss in the next class. So and then we will try to solve uh, some other mathematical problems. I will bring it from any books, and we'll try to solve it in the next class. First we will solve with that, and then we go forward the further any any problems or doubts do we have, then we can discuss about this. Okay, so that's all. To that we'll finish over here. Thank you, and then we'll see you in next class. Okay, bye. Bye bye.